All right, guys, welcome to another episode of Cuda Education. Today, I want to basically continue our discussion of an algorithm that I've been using to basically learn Vulkan. It's a series of algorithms. This is Cuda Education, and the name of the algorithm is triangle.cpp, and it is authored by a gentleman named Sascha Willems, and I'm using it to basically learn some stuff about Vulkan and of course teach everyone. So if you're interested in joining along, if you have a Windows-based machine with a Vulkan-capable GPU, you could definitely check out tutorial number 1 and tutorial number 13. The links are below. Tutorial number 1 will help you to install the Vulkan API on your Windows-based machine with a Vulkan-capable GPU. And then tutorial number 13 will help you with installing the examples, including this triangle.cpp example. So the topic of this video is basically trying to map out the synchronization tools that are used in the algorithm. So there are fences and there are semaphores, right? The algorithm basically generates a triangle on the screen. Okay, it's a triangle with colors inside of it. Then that's pretty much it. It's rendering a triangle, right? But the algorithm goes through a lot of various synchronization things in order to make it all happen, and that's what I want to kind of discuss in this next series of videos. I've been playing around with Vulkan for a while now, and I've been bouncing around with a lot of the examples that come with the package of examples that this includes. And I said, okay, I'll quickly jump into the triangle algorithm and cover the fences and semaphores discussion, synchronization in Vulkan. And I thought it would be a quick thing, an easy thing, and I've done videos on this before. Generally, synchronization, you can check out my other video. But man, when I dived into it, I realized that it was a lot of moving parts. So because it's a lot of moving parts, I I wanted to try to make it as easy as possible for everyone to follow. Okay, and so I'm gonna kind of take it slowly. Do some whiteboard stuff, and then dive into the code itself, right? It's a lot of things. So I want to just make sure that we're all on the same page and it's easily digestible. So focus on specific things of the algorithm, and this one is of course talking about fences and semaphores. All right, so as you guys should know by now, because you guys have been watching my videos, a fence is synchronization between CPU and GPU. All right, so we're gonna have our CPU, right? CPU, and then we have, let's say a dividing line, right? And then we have our GPU, okay? So your CPU is your just standard host processor, usually usually Intel, AMD sometimes. And then your GPU is like NVIDIA, AMD. Now Intel is creating GPUs, but that's your graphics processor, right? So the triangle algorithm basically makes a lot of draw calls, right? And it's a draw call that's basically initiated from the CPU and basically is being called to the GPU, right? So, you know, your typical computing, everyday computing is done through the CPU, right? So your word processor, your IDE, Visual Studio, what you type on your screen and all that stuff, that's all being done on, the CPU is making all that happen. The GPU is basically used for graphics rendering, parallel processing, and more intense stuff, right? So when you do a draw call, you don't just tell the GPU, hey, you don't just tell the CPU, hey, CPU, make this draw call, and then that's it, because you're gonna make multiple draw calls, right? Because you're actively rendering this triangle. So you need a mechanism in order to make sure that to communicate that, okay, the draw call has been initiated to the GPU, and then the GPU has a mechanism to communicate back to the CPU that the draw call has been finished, right? So if you don't have synchronization, you basically have, draw call, draw call, draw call, draw call, draw call, draw call, right? Draw call, and maybe you have one returning call, right? So in all of these, in 1 second or 2 seconds or 5 seconds, all the CPU is just continually, submitting draw calls, right? And then maybe the GPU can't catch up, right? Because it's easy for the CPU to submit the draw call, but maybe it takes more time for the GPU to actually do the drawing that the CPU is requesting. And what ends up happening is you have all these draw calls here, and there's no real relationship between the draw call and what's going on the GPU, right? The GPU is trying to keep up with all the draw calls that you're doing, and it becomes a great mess. So in order to manage this situation, what we basically have is a fence. Okay, so a fence is, in layman's terms and in just simple terms, all a fence is just reconstruct my computer system here. A fence is, I submit a draw call to the GPU, and then I wait for the GPU to respond to say that it's completed before I submit another draw call. You see what I'm saying? So I submit, I wait for the response that it's complete, and I submit again, and then I wait for another response, and then I might submit again, okay? And so on and so forth. So this whole relationship here is managed by a fence, which I've discussed in my previous videos. So it's not too much of a surprise, okay? So when we eventually go through the triangle algorithm, you're gonna see that we're gonna talk about fences, and these fences are basically, it's managing the CPU to GPU relationship, right? So nothing too crazy to understand with that. Let me see if there's something else I wanted to discuss about fences. Right, so we have this thing called VK wait for fences, right? So the VK wait for fences is basically when we submit the draw call, this is the VK wait for fences, right? So you're gonna see a function when we do the algorithm where we're gonna say wait for fences, and wait for fences is basically we're waiting for the fence to respond to say, hey, I'm complete, okay? So that's pretty much our fence, VK wait for fences. And you could look it up in the spec for yourself. Just type in VK wait for fences in Google, all one word, and it will come up on the spec, and it will tell you exactly what that situation is. So that's basically the fence relationship. It's it's pretty simple and straightforward. What kind of gets complicated just in general, and even in this algorithm too, is semaphores. Okay, so semaphores now, it's a whole nother cup of tea. Semaphores deal with let me just rebuild my computing system. Okay, so semaphores now deal with processes on the GPU. So you have like process 1, right? And then you have process 2, right? And maybe process 1 has to happen before process 2, and maybe you can't restart process 1 until process 2 is finished, right? So these relationships, the relationship and synchronization of it, right? Let's just say sync, right? This is the this whole thing is we use semaphores for this. Okay? So semaphores deal with two or more processes, or however, on the GPU. So remember, this is all GPU related. We've forgotten about the CPU now, right? We're just dealing with the GPU. Like I've said before, at the time of me investigating semaphores, there were certain things that were not available to the user readily in terms of what's going on. You basically tell the GPU, hey, these are two processes. This is what has to happen in order for when you're dealing with the two processes, these have to be in sync, or this has to be completed before something else can start. You basically build a relationship on the GPU between two processes, and you set it and forget it. You press play, you set it and forget it, right? And you don't necessarily always know the state of things on the GPU. Now, for the fences, for CPU to GPU synchronization, you could kind of query stuff. Now, I know the Vulkan guys, the Vulkan API guys, the Kronos group they've been updating the spec for Vulkan, so I don't know if things have changed since then. But as far as I could tell, it is you kind of have less information. You kind of set up the relationship between two processes, and then you press play, and that's it, right? And there's no, and that's pretty much it. You could just basically be rest assured that the relationships you set between the two processes are being adhered to, because you set up the semaphores and you submit stuff. And also declare the semaphores, right? A couple other things that before I get into more of semaphores where the real action happens. There are two, especially dealing with semaphores, but I guess with fences too. But these semaphore and fences, there is a signal state and an unsignal state. So a signal state means that like for example, process is complete, and then an unsignal state is saying that the process isn't complete, or it's not done yet, or it's not available, or something of that. You have this signal and unsignaled dynamic, right? It's sort of it gets mixed into the conversation of synchronization. So you might start a process, and then it's in the unsignal state, right? Which means that the process has not completed yet. And then once the process is completed, you get your signal state. So specifically for the semaphore relationship, we have two things called P weight semaphores and P signal semaphores. Okay, so you know, whenever you're going through your code, and of course when we're actually diving into the code, we'll see that these things being used. But you have as a parameter, when you're submitting certain functions and stuff, you have a P weight semaphore, and then you also have a P signal semaphores. So the P weight semaphore is basically, it's a stipulation saying that, hey, don't do this process, or don't execute on this command or command buffer or what have you until this semaphore, this semaphore ABC is complete, right? So that's what the wait piece of it is, right? We're waiting on a process to complete before we start our next batch of commands, right? So this is so wait on semaphore ABC before we before we execute on this process that we're submitting, right? This batch of commands that we're submitting. You also have a thing called P signal semaphores, right? And we could say this is DEF, right? So what signal semaphores is saying, hey, okay, we've waited for the semaphore is signal that it's complete. Now I'm going to do my process. And once I'm doing my process, after my process is complete, I'm going to signal DEF, basically put up a flag saying, semaphore DEF is now in a signal state, it's now in a completed state, it's now in a finished state, right? So that's what's signaling to the world that, hey, this is completed, you are now clear to proceed with whatever else you want to do, right? So this is the signal piece. So notice that if you have two processes, let's say process 1 and process 2, in process 1, we might have, hey, process 1. Now, these are commands in process 1, right? So we might say, hey, process 1, you cannot start process 1 again until semaphore ABC has been signaled, okay? Which means it has been completed, right? So process 1 is saying, okay, it's just going to stay here. It's not going to do anything until semaphore ABC has been completed. Now, once semaphore ABC is completed, process 1 is going to start. But hey, process 1, I know you've started now, but upon completion of your process, once you've done everything that you need to do, you're going to have to signal to the algorithm, to Vulkan, to everyone that you're completed, and you're going to signal by turning on this DEF, right? So you have DEF as saying, hey, I'm completing. So these wait and signal things, it's you could, the process 2 is going to still have a wait and signal also, but process 2 is going to be, let's say this is process 1. Let's say this is process 1, right? Process 2 might be, and sorry for my handwriting, but process 2 might be, we're gonna wait, so P wait semaphores equal, we're gonna wait for DEF, right? And then we're gonna signal for ABC, right? So you could kind of see where the two can be related. So this one is waiting for ABC to be finished, process 2 to be finished before it starts a process 1 again. And then this one is waiting for process 1 to be finished before it starts its process 2, and vice versa, right? So that's like the way I like to think of it. You know, I'm not gonna say that I'm 100%, you know, this is exactly, but that's these wait and signal semaphores. We're gonna tackle this in the algorithm. The reason I'm doing this video is to make it easier for you guys to follow me once I dive into the algorithm. Because if I just go into the algorithm directly, it's gonna be very hard for you to follow, and you're gonna be it's gonna kind of be overwhelming and stuff. So we have our wait semaphore and our signal semaphore. Okay, so that's another piece of the puzzle that I wanted to discuss. Now there is a situation on the fence side, so the CPU to GPU relationship, where basically Sascha Willems, the author of the triangle algorithm, he starts off for the fence process, right? Remember, we're dealing with fences now. He starts off with the fence being signaled to basically say that you know, the fences he initiates the algorithm with the fence being signaled, right? And why does he do that? Because he basically wants to communicate to the algorithm that, hey, you know, the process is complete and you can proceed with what you need to do, right? So the initial conditions for the algorithm, triangle.cpp, for the fence is initiated as a signaled in the signal state. All right, so that's you know, that's interesting to know, because what I did is that in the algorithm, for the fence, you know, as it starts off as a signal state, so it means that it's completed, and then the algorithm can say, okay, it's completed, so I can proceed with whatever I need to do, and then it resets itself. So, you know, maybe when it submits the draw call, then the fence is changed to unsignaled, and then when the GPU returns with, you know, that is completed, the fence is now what is it? So right, when it submits it's unsignaled, and then when the GPU returns, it's back to signaled again, right? So that means it's complete, and then it can proceed. So I played around with this fence. I was like, okay, we started off the algorithm with the fence being in the signal state. Let me let me change it so that the fence starts off with in an unsignaled state. Right now, I wasn't really sure necessarily how to make it unsignaled, but basically I kind of just like commented it out, you know, the signal piece of the fence creation. And I was hoping that the algorithm will just run but not show like a triangle or not show anything, but it actually, like, it runs. Like you could build the algorithm and run it, but it just kind of like it waits, and then it kind of like crashes, right? It just doesn't do anything, which, you know, I guess makes sense, because if the fence is created and then and the algorithm starts off in an unsignaled state, then basically what the CPU is doing is it's waiting for a change of the fence to the signal state, which basically means that, you know, what it's supposed to mean is that the GPU has finished with the draw call. But in the initial condition, when you first start the algorithm, right, when you start the algorithm, there has not been any draw call, right? And there has not been anything submitted to the GPU. So the CPU is just sitting there lingering, like waiting for the fence to be in a signal state so that it can proceed with what it is. But if it's the first time you're running the algorithm, there is no there was no submitted draw call. So the CPU is just going to sit there, wait and wait and wait. And in my case, it kind of just, the algorithm just crashes, right? Because, or the application crashes, right? Because it's just waiting indefinitely. Maybe there's like a timeout thing, or, you know, I don't necessarily, haven't gotten too deep into it, but these things are important. So, all right. So let's dive into another piece of the puzzle. So we're back on the GPU now. We're not really dealing with the CPU. The CPU basically is just to submit the draw call, right? And then all the magic happens on the GPU. So on the GPU, we have a thing called a swap chain, right? So we have a thing called a swap chain. Now, depending on who you ask, swap chain is 2 words or 1 word. You guys can tell me in the comments whether it's 2 words or 1 word, but I have reason to believe that it's 1 word, right? So we have our swap chain, right? And I have discussed this in previous videos, so you could check that out too, right? We have our swap chain, and all our swap chain is basically, it's I guess I'll just do it like this, right? So all a swap chain is just a series of frames or images, okay? So how do I want to do this? Okay, so it's just a series of frames. So think of it as like a picture frame, right? A blank picture frame. So we have a series of frames, and I'm not the best artist, but basically it's a series of frames, okay, that are lined up. Okay, now in our case, we'll get to that, but in our case, we only have a limited number of frames, right, for the triangle algorithm, okay? So it's just a series of frames, okay? So we have these series of frames. You could call them pictures, you could call them images, whatever you want to call them, but for our purposes, we haven't done anything with them yet. It's just a rectangle, pretty similar to the rectangle that's your monitor, right? Now, some of y'all have those curved rectangles and all that stuff, but let's just keep it simple. So, you know, a rectangle like that of your monitor, right? And it's just a series of images. And then what has to happen is that the Vulkan API, it lines up these images, and then these frames, these pictures, these images, and then what it does is it presents to the screen, okay? So I'm just gonna do this right here, right? And this is presentation, or present, okay? So we have our swap chain here, and then we present to the screen. So this is now your monitor. This is actually pixels on your screen that go to your eye. So you're somewhere over here, you're looking at your monitor, okay? So the Vulkan API has a bunch of frames, right, that are queued up. This is called a queue, right? A line of images that are lined up and then presented to the screen, right? And presented to the screen means that they're pixels that are arranged in a certain way with specific colors and all that stuff, and it's what your eyes see, right? The light is emitted from your monitor to your eyes, and then you're able to see the image, okay? So remember, these are frames. Now, you guys who are into video games and stuff, you know this all too well. There's a thing called FPS, frames per second, right? So these are all the frames that are being presented to the screen. If you have a very low frame per second count in your video game, that means the images are very stuttery, it's slow. If there's a guy running, he's not, running necessarily. You're not seeing a smooth transition of his legs moving. it's sort of jittery, it's buggy, it doesn't, it's not fast. If you have a very high frames per second, it's silky smooth. It's like, you know, beautiful, fast. You could see every bit of it. Your brain is getting a bunch of frames through your eyes, and you could see a silky smooth movement of images and stuff, right? These are the frames here, right? This is what this swap chain is, a bunch of frames, okay? So we're lining up these frames to present to the screen. The only problem with this is that we don't just want blank frames, right? We don't just want a frame. We don't, you don't go to the museum to look at a bunch of like picture frames, right? You actually want to see something in the frame, right? So this is where synchronization is important. There are two kind of states. A frame can be drawn on, and a frame can be presented. All right, a frame can be drawn on. What we like to call in computer graphics is render, right? And actually, the name of the function that's used in this triangle algorithm is called render. It's the render function, right? So when we render, we're drawing onto the frame. Okay, so it's not just a blank frame now. Now it has stuff on the frame. And then when we present, we're basically showing the user, we're showing you on your monitor what it is that's on the screen, right? I mean, we're presenting what's in the frame, right? We're presenting what's in the frame, right? So you have all these frames that have to be lined up and then presented to the screen, okay? This is where synchronization comes in. If you have a specific frame, let's say you have this frame, you can't be drawing on this frame and also trying to present the frame, right? One has to happen before the other. Or even more generally, one can't happen at the same time that the other is happening. So you can't be drawing on the frame and presenting the frame at the same time, right? One has to happen preferably before the other and all that stuff, right? So we need a process where we're basically taking images, we're taking frames, images, frames, however you want to call it, out of the swap chain. We're drawing something on it. We're putting it back into the swap chain so that it can be presented to the screen, okay? If it's being presented on the screen, obviously we're not drawing on it, all right? So this is where semaphores come in, right? So what are the semaphores managing, right? They're gonna manage, number one, drawing on the frame, and then number two, presenting to the screen, right? So we basically have to manage this relationship. We can't be drawing on the same frame that we're presenting to the screen, right? Now, this is the topic of discussion here for this thing, right? Drawing on the frame and presenting to the screen, okay? So these are our two semaphores. Now, in the triangle.cpp algorithm, right? In the triangle.cpp algorithm, we have a variable called I'll just put it up here, max concurrent I guess is it singular or plural? Right. Okay, we have a variable called max concurrent frames, okay? In the triangle algorithm, max concurrent frames. In this particular algorithm, the max concurrent frames is set to 2. So we don't have all of these. We don't have 1, 2, 3, 4, 5, 6, 7, 8, 9 frames. We don't have 9 frames. We only have 2. You could increase the number, and basically what Sascha says in the comments is that you could increase the number of frames. It's just the latency and stuff. It will increase because now you're managing more frames and all that stuff, right? I think at one point I did max frames to 0, but I forgot what happens when you do max frames to 0. I assume that it's just gonna be a blank screen, but I guess when we get into the code, I'll change the number of concurrent frames to 0 to see what happens. I assume it's just gonna be a blank screen because you don't have any frames to do anything, right? But I don't remember. So instead of all of these frames here, we just have 2, okay? So we're down to 2, right? I'm gonna say that this variable starts counting from 1, so it's just 2 frames, right? It uses the number 2, so I'm just gonna assume it's 2 frames, right? So that's all we got, guys. We don't have a bunch of frames. It's ideal on a certain level to only have 2 frames because it's less stuff to manage, right? It's less, yeah, that doesn't look good. It's less it's less moving parts, less things to manage, right? So ideally what we would want this don't look good, but anyway, you guys get the idea. Ideally what we would want, I'm not an artist, guys. I'm an aspiring programmer. I'm not an artist. Ideally what we'd want, you see now this is giving me problems. What's going on? Ideally what we'd want is we want one frame to be presenting to the screen and the other frame to be drawn on. And as soon as this frame is finished presenting, this frame is ready to be presented and this frame is ready to be drawn on, right? So we're doing an interchange with two frames, right? I was a little surprised when I first realized that concurrent frames was only 2. I thought that it would be more, just to give the application and Vulkan and the powers that be a sort of a buffer, just in case. But we're only presenting a triangle, right? So, I mean, in this day and age, GPUs are pretty powerful and fast, and they could draw a triangle pretty quickly and present and stuff. And when we run the triangle algorithm, you're gonna, I believe we get a FPS number. We get a frames per second number. So what that means is that when it's showing the triangle on the screen, it's gonna say, hey, these are the number of frames per second being shown to you, right? So even though we only have 2 frames, the swapping out of the frames is extremely fast. It's like, I don't even remember, but it's like 1,000 frames per second or something. I don't know. But this is what we have to manage, all right? This is what we have to manage. We have to manage these 2 frames, one being presented, the other one being drawn on, and then they swap out. So once this is being presented, there's like a clear value situation where you clear the frame and you put it back into the swap chain as like a blank slate, and then it's redrawn on, and then the process starts over again. So as soon as it's presented, it's cleared out as a blank thing, and then it's drawn on and all that stuff. All right, so we have semaphores. We have to draw on the frame and we have to present to the screen. All right, so you kind of get that idea. So I know it's only 2 here, but I'm actually gonna rebuild a couple more frames just to get my point across. All right, so we know we have to present to the screen, right? We know we have to present to the screen, and we know we have to draw, right? So we have to draw and we have to present to the screen. All right, so here's what we're gonna do. We're gonna have a whole bunch of frames, right? I'll just make them kind of indecisive now. What's going on? All right, so we have a whole bunch of frames that we're trying to present, right? But we need now a process to manage the drawing process, right? So what we do is we take a frame. Let's say we take this frame here. Hold on. Let's say we take this frame here. It doesn't really matter. All right, let's say we take this frame here, right? Let's say we take this frame here, and then what we're gonna do is we're gonna draw on it, right? So basically, we're gonna draw on it. You see how nice of a graphics engine I am? So we're drawing on it, right? So we take the frame, we draw on it, and then we return it to the swap chain. So we return it to the swap chain to be rendered to the screen, right? So anyway, all right, so this is our triangle here, right? So we take out a blank frame, we draw on it, and then we return it to the swap chain and present to the screen. We need a semaphore to notify the world, to notify Vulkan API that we have taken out a frame, we're doing stuff to it, and it hasn't, and what we're doing hasn't been completed yet, and therefore it is not available for presentation, right? This piece hasn't been done yet, so it's not available for presentation. So the variable, the semaphore that we use, the semaphore that we use is render complete semaphore. All right. So render complete semaphore is the semaphore that we use to manage this situation. So when a frame is taken out of the swap chain, right? When a frame is taken out of the swap chain, I assume this render complete semaphore will be in a unsignal state, and then once it's returned to the swap chain as being render complete, it's in a signal state, right? And then once it's in a signal state, then this makes it this process now, this presentation process, it makes it available to be presented to the screen. So remember we had the wait semaphore and the signal semaphore. Remember that discussion with the two processes? That's kind of what's going on here. So this process is waiting on render complete, right? And then when this frame is being presented, the drawing process is waiting on the present complete semaphore, okay? So we have, but I don't want to confuse you. Remember we had our two processes. We had a waits semaphore and a signal semaphore, right? So here, before we could even get a frame in order to draw on, we have to make sure that this guy is finished, right? Because again, we can't take a frame that's actively being presented to the screen. So this process is going to wait on present complete. Well, you know what? Let's not even go there. So we know that this is render complete semaphore, right? So we take an image, we take a frame out of the swap chain, we draw a triangle on it, and then we return it, right? And the render complete semaphore is what we're going to use to say, hey guys, this is the rendering has been completed, the drawing has been completed, and it is now available for presentation. Now the present, so that's the render complete semaphore, okay? Now the present piece of the equation has another semaphore called the present complete semaphore. Okay, so this guy, I'll just do it up here. I'm sorry it's smaller, but you guys can will understand. So this is the present complete semaphore, right? So we have our render complete semaphore and our present complete semaphore, okay? What is present complete semaphore? Present complete semaphore, basically it's on signal and signal, but basically it's saying, hey, we're actively presenting the frame and it's not available for anything else. Once we're finished presenting the frame, then you could do whatever you want to do with it. But until this is finished, this semaphore is going to be in an unsignal state because it's presenting to the screen. All right. So we have render complete semaphore and present complete semaphore. And that's pretty much it. So, you know, you're going to see a big triangle on your screen, right? What is it? 4K, 8K, 1080p? What you guys running with right now? What's the max resolution and all that stuff that your monitor can do, right? That's what you're gonna see. But while this is being presented, present complete semaphore is managing it to tell the application, tell Vulkan, tell the GPU, tell everybody that, hey, this frame is now actively being presented. It is not available for anything else. Same thing with this guy. This guy is actively being rendered to. This frame is actively being drawn on, rendered to. It is not available for presentation. So that's the duality that we're managing here. And that's what semaphores are for. All right? So we got our fences and we got our semaphores. What's fences again? CPU to GPU relationship, synchronization. What's semaphores? Semaphores is GPU to GPU relationship, synchronization for GPU to GPU processes. All of this is happening on the GPU. The swap chain is on the GPU. Presentation is happening, you know, through the GPU, right? It's sort of being done on the GPU. Vulkan API. Vulkan API kind of lives on the GPU, right? That's what it is. Again, I'll reiterate the reason why Vulkan is so complex is because in order to do all the fancy video games and all the crazy applications that you guys like to do, in order to do those things, it requires a lot of communication, a lot of options, a lot of parameters, a lot of signaling and unsignaling, a lot of things to manage. You have to manage memory, you have to manage hardware resources, you have to manage synchronization, you have to manage the different colors that you want rendered to, you have to manage the different lines that you're using to render. You know, it's just a multitude of things. And the big innovation with Vulkan as opposed to OpenGL is that Vulkan allows you to make a lot of changes yourself. Like you could micromanage this thing down to the core, right? And that gives the programmer a lot of power. So this is the triangle algorithm. Yes, it's, you know, it's a lot of moving parts, but we're going to work our way through it and we're going to be disciplined about it, and we'll get through it and we'll figure out all the other stuff. But yeah, guys, so what, you know, next video when we dive into the triangle algorithm, all of this stuff isn't going to be foreign to you. You'll kind of have an idea of what I'm talking about. Remember, this is the max frames thing, so we're only dealing with 2 here, where, you know, we got a whole bunch of frames, but really the max current frames is only 2 that's required to make a simple triangle. I'm gonna assume that if it was a way more complex situation that we're presenting to the screen, that we couldn't just do it with two frames. We'll have to have had other frames queued up and all that, but that's just me guessing. I don't know for sure. Let me see. Do I want to talk about this real quick? All right, so there is a function. There's a function in the algorithm called acquire next image. I haven't fully investigated it, but basically that acquire next image function is it's basically acquiring the image from the swap chain. Okay, so we're gonna see it when we do the investigate the algorithm, but acquire next image is gonna be when we pull a frame from the swap chain. Okay, again, swap chain is 2 words, 1 word, depending on who you ask, what have you. So right, render complete semaphore and present complete semaphore, those are things that are man-made. You know, Sascha Willems created these 2 variable names, right? To, you know, these are what he called the semaphores, and it makes sense. Present complete basically means that the presentation has been complete, and render complete basically means that the render has completed. Render is just a fancy name for drawing, right? You're rendering a scene or you're drawing a scene or what have you. That's it, guys. Thank you for watching Cuda Education. Remember, if you guys want to have these algorithms running on your machine, Windows-based machine with a Vulkan-capable GPU, get tutorial number 1 and tutorial number 13. Also check out the other videos that I have in this series. I'm going to continue to be working through the triangle algorithm, because I realize it's very important for people to understand this stuff. And once you get the triangle algorithm, then, you know, the rest of Vulkan, it's a little bit easier to just you know, you run faster, and you can learn, you know, you could sort of get a better grasp of everything else and do all the fancy stuff that there is to do in Vulkan. But we just have to hold our feet to the fire and get through this process here, and then we'll be all right. So anyway, guys, thank you for watching. This is Cuda Education. Get a bunch of your friends together, learn this stuff together. It's cool to play video games and stuff, but learn something too. Learn how to make your own video game, right? Start the process. Nothing that's worth achieving has ever been done overnight. It requires a process, and you just have to invest a little bit of time in it every day. It's like a drop in the bucket. You just invest a little bit of time every day into something, and you'll be amazed at how far you reach in a year or 2 or 3 or 4 or 5 or 6 or 10. But that's all right. We'll continue working at it. All right, guys, let me know what you think in the comments below. Thanks for watching.